Mic test. actually, in your first lecture, there was some maybe about some local thing and global thing. Right?
Okay.
Actually, when I learn about the Mendel curve and some world identity, I just understand that just some trick to pull out to extract some conservation rate. I mean,
Yeah.
right? This is just everything
Oh,
in
yeah,
just
but
QFT.
so in QFT, yeah. So, but the implicit assumption in that meta theorem is that the symmetry action is defined pointwise. So you don't write symmetry action which involves the one field value at one point at the field value at I mean that's the translation, but it's more like the pointwise action, and that so yeah, and what you so you basically use that fact to derive all those word ideas. That that's where this locality of QFT just means that if QFT is defined on a manifold and in a nice way, and um, so yeah, that was the yeah, yeah, thanks,
Yeah,
thanks.
yeah.
May I ask some question?
Yes.
Yes, I guess I missed yesterday something in yesterday's talk. Um, when you gauge the half space, so we end up with some topological operator at the boundary of the mesh.
Yeah.
And what does the Z operator actually do to the operators that cross that boundary? So what is the say symmetry action
Yeah,
of
yeah.
the
So that of
operator?
course depends on the theory to theory, but what can happen in general is that so this is in the example of Euler model that you have this Kramer-Swaney duality line, and you have say the spin operator that measures up or down
Right.
the operator, and if you push this topological operator crossing this
The boundary, yeah.
yeah, then we have to go um, yes, yes, Alpha. Like this.
Sound flagged.
Uh,
Oh, okay. So let's wait for a few minutes. Okay, so this will be welcome back. This will be our last class, I guess, by Kantaro Omori, and he will give a last lecture. Thank you.
okay, so thanks for you guys surviving until the end of school, and so as a last speaker, I have obligation to let, uh, to have a time to thank all of the organizers that who brings this great workshop until the last lecture. So let's give them great applause. Okay. Okay, so let's start the last lecture of this school. So I'm going to talk about what I call non-invertible chiral symmetry. And so which mainly based on the paper by Justin Cady, myself, Yukichi Zheng, and Ichi Choi. That one is 2021, and also the other two papers. One is by Ichi Choi, Hoda Lam, Shuhen Shao. The other is Craig Calder by myself. Okay, so I said that for the construction of non-invertible symmetry in dimension greater than 2, there are a few ways of constructing such. And one is half space gauging that I talked yesterday, and there are a few others, and one of them I'm going to talk, which is a stacking TKFT on the surface, roughly speaking. And so here I focus on a particular example, which is 3 plus 1 dimensional massless QED. Okay, so nothing fancy, just the usual massless QED that every textbook talks about. You want gauge theory, and with fermion. You can of course think them as electron and positron. Okay, so and this theory classically has a chiral symmetry, which rotates, say, one helicity mode, but not the other. Okay, so of course this U1 gauge symmetry acts anti-diagonally on left and right, but the chiral symmetry is the classical global symmetry acting on only one of them. And there's an extremely famous fact that there's an anomaly in the symmetry. So there's ABJ anomaly. Coming from triangle diagram. So this J chiral is a net current for this classical symmetry, and these are gauge fields, and this is fermion. And this diagram gives you a correction, or in other words, there is a anomalous transformation from the Jacobian of the path integral that the conservation law of this chiral symmetry is modified by FF mu nu rho sigma and contracted by epsilon symbol. Okay, so this often says it's often said that this effect quantumly breaks this symmetry. So what do so from the conservation law, that's one way to see that the divergence is no longer 0, and rather depends on F, which is other dynamical field. Another way of saying it is that if you consider this symmetry operator, that is exponential of j chiral on the codimension 1 surface. But this is non-topological if you define it. Okay, so that's because if you have two surfaces, one is the deformation of the other, then so repeating the argument, the difference is using the Stokes theorem, the integral of divergence in the volume, which is now f h f, which is, and this is some dynamical field, so this is some non-trivial operator in the theory. Okay. Now okay, so that's the usual story, but now I claim that there is a way to rescue this symmetry. Although, of course, we have to give up something, and what we give up is the invertibility. Okay. Okay, so how to do that? So one possible attempt to rescue the symmetry is to modify the current. So modification of current to by some number with a maybe just mu neural sigma explicitly write the index. Okay, so this kind of modification, okay, then it seems that so at least formally that cancels out the right hand side. However, this is not gauge invariant. Obviously from I mean gauge invariant under gauge transformation of the photon. Okay. Okay. This is the usual remark that you probably find in textbook. Okay, but I was emphasizing the role of this symmetry operator, not just current. So let us exponentiate it just modified symmetry operator. If we so it's still not quite work, but if we integrate this modified version, then what we get is the unmodified j. I should yeah, I am writing this the modified version of j mod, and then well alpha sigma 1 a dA. Okay, I just integrated and exponentiated, but this looks better because now this integration looks like a Chern-Simons action. Okay, so good. However, this so once you In other words, once you integrate, then this thing is invariant under local gauge transformation. However, for arbitrary alpha, for a generic alpha, this transformation action is not gauge invariant under a global gauge transformation. So that is well-known story. So this does not work yet. If you can tune the alpha so that this is globally gauge invariant, but that means that alpha is the integer multiple of 2 pi. So then then it doesn't it trivially acts on the field. So what to do is, first, to go further, first it's good to set alpha equals to some rational number. Times 2 pi, of course. And for simplicity, we set further p equals to 1 for simplicity, but this is just a technical assumption, and you don't need it. Then, so here we get 2 pi over q of ADA. This is not sorry. So I should have wrote 2 pi here, and then I erase here. Sorry. Yes. Okay. So I'm fixing that coefficient. So no, I think this is 4 pi. Whatever. Then, so this is not invariant on the global gauge transformation. Okay, so, but this problem of like having some effective action of photon with wrongly quantized Chern-Simons coefficient appeared in totally different context, which is fractional whole state in the condensed matter physics. So this is supposed to nothing but if this sigma 1 is the wall sheet of the fractional whole state material, then this is nothing but the effective action for the you expect for a fractional whole state. And in that context, of course, we know how to regularize gauge invariantly, and that is a non-trivial topological field theory living on the fractional whole state. Okay, so we can just follow. So this is effective action. I should write of, let me erase, for fractional quantum whole state. Okay, so we can just borrow the answer from the well understood subject, and what you do is to introduce new degrees of freedom on So this is a new gauge field. On this operator, this is three-dimensional submanifold in your spacetime, and we introduce new degrees of freedom on it, and write down Chern-Simons term for this new gauge field. Okay, this is U1 level P. Sorry, U1 level Q, and let the new field couples with the bulk. This is bulk photon. Okay. And this is I think here I should write 2 pi. Yes. Okay. And this side is completely gauge invariant for both the A and, well, from this expression, it's obvious that the gauge invariant under the gauge transformation for photon, and it's also gauge invariant for the gauge transformation for the new field. So this is U1 gauge field. Yes, yes, yes. Yes. So here I don't have time to give the full detail proof of why this works, because then I have to introduce all the machinery of correctly treating the U1 gauge field. But rather, I just give you why, morally speaking, the two sides are the same. I mean, the one side, left hand side, is ill-defined. Right hand side is well-defined, but we can just loosely treat the right hand side and derive the left hand side. Okay, so the locally, the EOM for A, small a, is like Q. Yeah, my Q is just this is some integer, and that is the A. And this is a wrong procedure, but we solve this as by this. Then substitute then S equals to, yeah, we just substitute this to this action, and we get this. Okay, we cannot conclude that this from this for globally, for the globally non-trivial configuration for small a and large a. But when both sides are at least just local, then this reproduces the effective action we need. Okay. So as a conclusion, we get a topological operator, which I call D 1 over Q, and on sigma 1, that's, maybe I just write this way. The naive thing times U1 level Q Chern-Simons theory on sigma 1. And pitch couples with the bulk photon with that way, in that way. So this is, I claim this combination is topological. Yeah. So one way for someone knows about this one form symmetry anomaly for this TKFT, I just comment that one can regard this construction as that the anomalous contribution coming from this part when you deform this your surface is cancelled by the anomaly, one form symmetry anomaly, coming from the U1 Chern-Simons theory, because this capital F behaves as a one form symmetry background for this U1 Chern-Simons theory. Okay, so as a from the paradigm that every topological operator corresponds to some kind of symmetry, we get a new symmetry. So this is a symmetry. Okay. So now we can regard the ABJ anomalous chiral symmetry in QED as a symmetry. However, the symmetry is non-invertible. So to see that, we think about again this fusion. Okay, and this is just D minus 1 over Q. Okay, and that naive part, that integration of J just cancels out. So we only have the U1 Chern-Simons theory level Q and U1 Chern-Simons theory with level minus Q. And this is on sigma 1. And of course, this is some non-trivial TQFT. Okay, so this is not 1. Now, this is not a random TQFT, but there is a this thing is isomorphic to ZQ level 1 gauge theory in 3D. That by Shin Lam Zaibag. But this is literally just, oh, sorry. So this is kind of BF theory. Okay, so that's like A dB plus Q times B dB. This is just rewriting, linear change of variable from here to there. So nothing difficult. Okay, but the point is that this BF theory can be regarded as a kind of discrete gauge theory, that the gauging of ZQ symmetry acting trivially on trivial theory. Okay, so this is actually a condensation, but this couples with, of course, couples with this photon. So we can further rewrite this. Explicitly write down this partial function for the gauge theory coupled with the bulk photon, and what you get is, maybe just explicitly write this. So Q over 2 pi F of S, where in however there is a okay. So you can rewrite this gauge theory partial function as in this way, where you sum up over this operator, which is nothing but the one-form symmetry, magnetic one-form symmetry, operator, and summing over all the ZQ cycles, so 2 cycles, in your defect wall volume sigma 1. Okay? And, well, technical remark is that in this case there is a, because of the here twist, or this term, there is a modification by triple intersection of S inside sigma 1, which is some detail. So this thing, in other words, is a condensation of magnetic one-form symmetry. Okay, there's a different condensation with different twist. There's a non-trivial twist, but anyway, it's condensation. Okay, so well, yes.
Okay, this is not very important detail, but why is it called level 1 and not level Q?
Oh, thanks. It's level. Let me recall. Level Q. Yes. Thanks. Yeah. Level 1 in bosonic, but in their notation they use the not this notation. Sorry. Yes. Thanks.
Oh, okay. Thanks.
Yeah. Let me see. But sorry. Let me back up. So sorry. I should wrote Q here. So in in BF theory language this. Well, I'm sloppy about the coefficient, so I cannot be really serious. But yeah, this. But here, sorry, right now I'm not sure that the correct notation that Shinram Zyberg hired, but yeah, the correct twist is this. Sorry, yeah. Okay, so let me rewrite. I mean, so this equation is so important. So the condensation of magnetic one-form symmetry. Okay. One comment about the condensation, the word condensation, and this word is invented in the condensed matter physics. So it's does not quite align with the nuance of this word when we use in the HepTH community. And so when we say condensation, it's more like some field develops vacuum expectation value. So it's like dynamical condensation, the spontaneous condensation. And here it's more like that it is a condensation of some topological operator or topological defect. So it's not, the condensation is not really spontaneous, rather some experimentalist or Gedanken experimentalist condense the operator to form the higher dimensional object. Okay, so that's the thing. Just a comment. And so coming back to this equation, so one thing we observe is, so this is just roughly speaking sum over the one-form magnetic one-form symmetry generator, and this is two-dimensional operator. Okay, so this is not non-trivial operator, but it acts trivially on local operator. Okay, because this whichever cycle you choose, it cannot non-trivially link with local operator because of the dimensionality. So as far as local operator is concerned, and your manifold, your space-time manifold is very simple, then you can ignore the right-hand side. So from that way, you can get the selection rule for local operators on flat space or S4. So starting from some local operator correlation function, S4, but you put some small ball of this topological operator. Okay, and one way, so you can just shrink down to a point here, then you get some number times this this is non-zero number times local operator correlation function on S4. But then we can also enlarge this small ball towards the infinity. But when this D cross the local operator, okay, then from the naive, so D involves one over Q 2 pi. D involves the usual natal charge, so you get the chiral charge. Okay, so you get the chiral charge. Chiral charge. And then Q over 2 pi. Here, and then you shrink this at the infinity, so you get the same number there, and the correlator. Okay, so this number and this number is the same. You just cancel, and you just get the conservation of chiral charge. On flat space or S4. And so, yeah, I should have said that. So this part D also involves this U1 level Q Chern-Simons theory, but which does nothing when it crosses through the local operator and just give you some number here and there, but it cancels. So yes.
Yeah. So if you take D times D or D times D bar,
Yeah.
so you get the condensate, and that does not act on local operators.
Yeah.
But I didn't understand how a single D acts on local operators.
Oh yeah. So I should, I should have said in that way. So yeah. So this thing is U1 level Q Chern-Simons theory. But this has nothing with this couples with photon through F, but this local operator it doesn't create any non-trivial F from. So yeah, this part does nothing when D crosses local operator. So you can in this business, you can just ignore this part up to some number get here and there, which is just a partial function of this TKFT that cancels. So you can get S4. Now, picking S4 is important. If this is torus, then we can try. I can try to do this, but then there's no infinity. Infinity is not the point. The infinity has more different shape. So when we shrink, then we get different contribution from here. So we cannot say the conservation on T4. But on S4, on a simple enough topology, then we can say.
On S4, I guess the total charge should be 0. Is there some super selection rule? Because it has
Yes. So this is a selection rule. The total charge is So by this, if this is total chiral charge, and
right.
if total chiral charge is non-zero, then you can pick. This Q is arbitrary integer, so you pick some. No. Of course, I should say 2 pi over Q. Sorry. You can pick Q large enough, then you get this is itself times non-trivial phase, and the only solution is that the correlation function is 0. So this means that total chiral charge has to vanish for this correlation function being non-vanishing.
Okay, thank you.
Okay. Good. So, well, so this leads to some selection rule in scattering amplitude, and for example, so in fermion scattering in QED, up to the correction by the electron mass, the helicity, this chiral charge is nothing but a helicity of electron. So the helicity of fermion are conserved in the QED massless QED scattering, and which is of course very well known from the very old time. So more physical explanation of the same thing is that what ABJ anomalous symmetry in general is broken by instanton, and this can be seen by the anomalous conservation law. And however, for U1 gauge group, there's no instanton solution on R4 or S4. No solution with the non-zero instanton number. Okay, so therefore there's no violation. Okay. So that's a more conventional way of explaining it. And also on other topology, on T4 or T2 times T2 or whatever, there are solutions for with non-trivial instanton number. There are backgrounds for photon background for the with non-trivial instanton number. Therefore, we expect that this chiral symmetry does not, is naively broken, and we do not have a conservation law of chiral charge, and that can be correctly reproduced by this non-invertible topological operator. Okay. Another point is that here the gauge group being U1 or being abelian was crucial. So no, not applicable. So the construction of this D, this operator, it cannot be generalized to non-abelian gauge group. Where it fails is the first part that this F, for non-abelian group, FHF is not really the D of, small d of Chern-Simons field. So that's fails. Yeah.
Excuse me, there is
Yes.
a question from online audience. The question is, it looks that there is an ambiguity for the total chiral charge. I mean that the total chiral charge can change under mode Q. Is it okay for the conservation law?
This is, I couldn't really understand. So which feature ambiguity in where? Is it about the construction of D? Sorry. Maybe I read.
I guess because it is on the phase, so you can always shift the phase by 2 pi I. So and there is a q in the denominator, so it shall be defined on some integers mode q. I think that is the question.
Integers mode. Oh, so yes. So here, for fixed q, of course, you cannot exclude the case that the total charge is multiple of q. But this q is your choice. So this holds for any integer q. So you just take the large enough q, then this is non-zero. I mean not non-integer. Okay. So how many? 20 minutes? 30 minutes. Good. Let me see. Well, I don't have much to say. So coming back to this equation. Okay, so we learned that this thing behaves as if just usual symmetry on for local operator and on a flat space or on S4. Yeah. However, if once you include some line operator, then this behaves in a particular way, because okay, so the right hand side is a magnetic one form symmetry. So this has something to do with the fifth line or the monopole. I mean, which is just a monopole world line. Okay. So you expect that something happens when you include the fifth line in your coordinator, and that's indeed the case. Okay, and so let's think about how this operator, topological operator, acts on the fifth line. So we prepared some fifth line with charge m, magnetic charge m, and here I put the topological operator and bring in this way. What happens is that so here we have Tm and D pass through D1 over Q, but then here this is
Can you use white color because it's very hard to see the blue?
yeah, it's very hard to see
yeah.
blue.
Yeah. Just
Maybe
for the
there's a
letters,
yellow,
yeah.
I guess. This is tiny. Let me find. Yellow is better. So, and I should say, this is 1Q. So a way of understanding it is that here, this is on heuristics. But so across this D, the chiral component of a fermion gets a sign, gets a face, and you learn that by nothing but the ABG anomaly, this amounts to give shifting a Taylor angle. And okay, so by this amount, okay, and here we have the fifth line with non-zero magnetic charge. So what happens? Sorry, here, M. What happens is that is a Witten effect. But from here to here, only a fractional of 2 theta shift by fractional 2 pi. So you get fractional. This monopole gets a fractional charge in general. And the Wilson line with fractional charge, electric charge, is not a genuine line, but rather understood as a boundary of U1 magnetic one-hot symmetry. So that's F. And here 2 pi I over Q. Okay. This just means, I mean, in a sense, this and this is double counting. So this just means the boundary of this guy. Okay. And the boundary is not topological. So this is an analog of the Cronus-Vannier duality line acting on spin operator in 1 plus 1D. So 1 plus 1, the Ising model. So Ising. So there you have sigma and n, and that is when this Cronus-Vannier pass through sigma, you get mu, this is disorder operator, and in between you get just a Z2 symmetry operator. This is Z2 symmetry operator. Oh, I should have used yellow. Okay, so sigma becomes the disorder operator, living at the end of the usual invertible symmetry line. Here, when D acts, non-invertible chiral symmetry acts on the top fifth line, this top fifth line becomes some operator living at the end of the invertible one-form symmetry generator. So that's the action. Okay, and this kind of the action is a hallmark of non-invertibility. Any question so far? Oh, so I should say that, so because of this funny action, on the fifth line, if you consider this kind of correlation function involving the fifth line. Of course, on the infinity, you also insert the inverse of this. Anyway, you this kind of correlator, and if you do the same thing that you inserting a bubble, the small ball of D, and inflate it, but you get some just funny configuration. Maybe just so. You still get the charge here, 2 pi I over Q times charge, chiral charge, of course, here, but you get some funny configuration here towards the infinity, and therefore you cannot say, you can equate this and that, but you cannot say anything about this itself. Okay, so no conservation of helicity with under the presence of monopole. Okay, so this is called monopole catalysis. And so phenomenologically, what you use this kind of thing is, of course, this is also known. I'm just rephrasing in terms of the new topological operator, but so phenomenologically, you use this fact to that in so by assuming that there is a monopole in our universe, then this process particularly induces the catalysis of proton. So if there are too many monopoles, then there's going to be no proton in the world, and we shouldn't be exist. So that puts a bound on the density of monopole in our universe. Okay. So sorry, say again. Yeah. So here I put the ball of D. Yes. That's what you did. Yes.
So original multiple catalysis comes from static monopole or dynamical monopole.
Oh, so of course, in the phenomenological context, the monopole is supposed to create it dynamically. So, for example, in the proton decay context, it should come from the Higgsing of GATT to standard model, for example. Yes.
But so the original monopole catalysis and I'm confusing about the relation between the original monopole catalysis and this monopole catalysis. So it is originally dynamical monopole, and this is just a line operator.
Oh yeah. So, but you can regard this as a particular line. So this is an IR argument.
Yeah. Right.
That
Right.
So if you have a monopole coming from dynamically generated at some early history of our universe, and you assume that there is a stable monopole, and then in the IR viewpoint, it behaves just as the fifth line.
Right.
Okay. So
So you regard it this total line as the IR limit of the early universe's dynamical monopole.
Yes,
right?
yes,
Okay.
yes.
Thank you.
Now, one thing I probably fails to say it, just remark, is that so this really very similarly looks like the fusion law we get from half gauging, and indeed we can also get the same operator from the method of half gauging. So that's one thing I failed to say. Now, how many times do I have? Okay. 70 minutes. Sorry, so next, I'm come back there. Yes.
So you showed the product between d1 over q and the d bar 1 over q. Is there something interesting? I mean, if you take two generic operators, is there some interesting algebra?
It's interesting. So yes. So that's what I and Christian and others working on. So there's a So I only talked about this product. The Francesco's question was about I only talked about this product, but of course there's a more general version, the P over Q. So you can of course think about this kind of thing, and you can also think about the associativity, or like P double Q prime and this or that, and relationship between two, and all of that, and yeah. So there's going to be interesting story, I believe, and now working on this F symbol relating the two way of composing these. Yes. Yep. Yeah. So briefly speaking, the general product, or more generally the general non-invertible symmetry on this in 3+1D. So you get some sum, but here coefficient is not the number, but this is again some TQFT. So this is 3D TQFT. So in higher dimensions, it's like that the fusion rule has TQFT coefficient. Then there's F symbol governing the associativity. That is a topological interface within the 3D TQFT. So that's a structure. Okay, so that was comment. Okay, so now let me talk about the broken phase. Okay, we can also think about the broken phase of the symmetry. So to go to the broken phase, for example, we induce scalar which is, U1 neutral scalar, and give a wave. The scalar okay. Then yeah. So of course we assign the chiral charge. So I write this way. So the chiral charge. So to preserve the chiral symmetry, we assign the chiral charge with the chiral charge to phi. Okay, so then by giving a wave to phi, we get we go to the broken face of the symmetry, and the IR limit, what we get is a free Maxwell theory. This fermion gets heavy, and energy mode, which is a phase of this capital phi, now goes to mode. Okay. Okay. So here we have this modified topological operator in the UV. So the same thing right here. So the same thing should exist in the IO, and so this is another way of like saying this anomalous conservation law should preserve. Okay. Now, why? Because this is in an avatar of this topological operator or vice versa, and it's clear that the topological operator doesn't care about the scale, so we clearly do have the same operator in the IR, and therefore we expect the same conservation law. By the way, here this chiral symmetry acts as a shift of this Gaussian mode. Okay, and to reproduce this, you need the axion coupling. So this is axion coupling. Okay, that's a convoluted way of well-known fact, but but purely the point is that this argument is purely symmetry argument now. So this is particularly provides the symmetry argument for the pi naught gamma gamma amplitude, that the dominant contribution coming from this kind of axion coupling between the neutral pion and FF. So this application of post diction is found by Choi, Lam, Shao. You have 10 minutes? Yes. Okay. So good. I'm about to finish. So last thing I want to talk about is so here I talked about the spontaneous breaking of this chiral symmetry. Now let us consider the explicit breaking, and there's a interesting way of breaking this symmetry. So I rewrite this equation, and so this part right hand side involves one form symmetry. So if you break one form symmetry explicitly, then this equation, so you lose one form symmetry, then through this equation, the chiral symmetry should also be broken. Okay, and so one way of breaking one form symmetry is having explicit to fifth line that I already discussed. the other way of breaking magnetic one form is having dynamical monopole. Okay, so from this equation, we expect that dynamical monopole should induce the chiral symmetry breaking contribution. So in diagram, schematic diagram, that's like the monopole coming like some the monopole loop generates the chiral symmetry breaking term. Okay, and so this is non-perturbative effect. So this is non-perturbative because the loop of the monopole so this contribution is like proportional to the world line action of this monopole. Rough estimate of it is like mass of monopole times the core radius of monopole. For this loop to make sense, this loop should have a size greater than the core radius of monopole. So this is the rough estimate. Okay, so to get the dynamical monopole, one way to having a dynamical monopole is to UV complete your abelian gauge theory to non-abelian gauge theory. So some non-abelian UV completion that gives you QED, some through Higgs, some Higgsing mechanism. Then you get the fifth Polyakov monopole. And we expect that this, just from fusion law, we expect that there should be some chiral symmetry breaking contribution of this form with this non-perturbative weight. And on the other hand, here we have UV instanton. So I said that in QED there is no instanton in flat space or like point-like instanton. I mean instanton whose configuration is not to be around the point, but in UV no-abelian gauge theory, of course there is. Okay, so there's a new UV instanton contribution which is the fifth vertex. That some instanton and which also violates the chiral symmetry. So natural conjecture is that the two are the same. So this in this Higgsing mechanism, this instanton contribution should be from the IR viewpoint should be thought as a monopole loop contribution, and indeed, so this thing is of course suppressed by instanton action, and you can like the order estimate, the instant action is like 1 over g squared, where g is the UV Yam's coupling. And here, you also substitute these two numbers from the monopole to fifth monopole to fifth Polyakov monopole solution, and it's also like g Yam squared. You can also you can better matching, and here you can assume that the monopoles are BPS, and if when you sum up over all the dions, not just monopole actually, so you also sum up over all the BPS dions, then by you can show that here that contribution matches with the BPS instanton. So yes. So we use this. So obviously I don't have time to talk about this, but we used this insight to construct a neutrino mass model. Where this neutrino mass is generated by some monopole, not the QED monopole, but some monopole, or some instanton in the UV theory. So that's I did with Koren and Sang Hon. Oh, I should. Cordova is the first one. Sorry, Cordova, Koren Hon, and myself. Oh, I made a mistake on the alphabet, which is very difficult. Okay, so that's one thing, one application. Okay, so yeah, so I've said almost all of what I've planned. Yeah. One. Okay. So another recent development I want to introduce you is about axion QED, where the axion Maxwell. And axion Maxwell, here there is an also non-invertible one-form symmetry. So far I've been talking about the non-invertible zero-form symmetry, but in this theory there also is a non-invertible one-form symmetry, and the construction is very similar to our case, by just having anomalous symmetry, naive anomalous symmetry, but stacking other topological degrees of freedom to cancel the anomaly. So this is by Choi Lam Shao, and also Yokokura. Okay, so I've said everything I planned. So for in this story of non-invertible chiral symmetry, I think it's significant that now we have a way to treat this ABG anomalous symmetry in abelian gauge theory as really a symmetry, and we know exactly what we mean by that. And we can also reproduce some interesting facts about this chiral symmetry in QED through the point of view of topological operator. So I think this is very beautiful, but still kind of we lack of striking application. Well, we tried here, but I want to see more application to come from this direction of thought. Okay, so I stop here, and thanks for your attention.
Thank you. So, any questions?
So yes, so I personally haven't studied much about 60. So yeah, I don't have much to say, but in 60, 2,0 theory is a kind of similar to the RCFT, and from that viewpoint, and to the RCFT has a very rich possibility of non-invertible symmetry, not the type of just half gauging or this kind of stacking construction, and they are more general. So maybe they're in 60 theory because of its relationship to the 70 Chern-Simons theory. Safety of Chern-Simons theory, there might be a more rich candidate or examples of non-invertible symmetry, and that's very interesting to study. Yes.
Yep.
Oh yeah. Also 1,0 has it's about this. Yeah, the same thing. 1,0 is also naturally thought as a boundary of 70 Chern-Simons theory. So the same thing. In some cases, I think no. Yeah. Yes, but I'm not super familiar with it.
So I think I missed the point. So what did you conclude about the neutrino mass model from this symmetry perspective again?
Oh yeah, so here just okay. So this neutrino mass model is coming. So here the neutrino mass is kind of small. So in our model, this neutrino mass coming from the UV instanton or the fifth vertex. And yeah, so we could cook up some concrete model. And yeah, well, the conclusion is that there exists such a model, and yeah, so we haven't yet checked this texture of the neutrino mixture. The mass matrix is just about the generating the mass of the correct order, but at least that's possible. And yeah.
Okay, thank you.
Any more?
From the perspective of ADS safety correspondence, there may be a similar story in gravity for non-invertible symmetry. Do you have any idea about that?
So there's including Francesco's works, there are ideas, to how to interpret this non-invertible symmetry or realize non-invertible symmetry in the dual. So how to see it in dual. So yeah, so that's basically the brains living in the bulk, which does not intersect with the boundary, and that those are the what corresponds to the topological operators, and it's very not. And for this type of non-invertible symmetry, these are TKFT on the topological operator comes from the Vesizumino term on the D brains, so that's very nice. story, and so there's a way to interpret this in the gravity dual.
Any more questions? Any from Zoom? No? All right. Let's thank the Cantor again.
Thank you.
So,
Let's thank organizers again.
well, but I guess most important thing is that you guys learn something useful out of the school, right? I mean, all this is for you guys. So I hope for you look at what you learned and then digest it and produce something useful or interesting. So for that, let's thank speakers, all the lecturers. Again, let's thank. And then we have steps, maybe, and also some interns who've been. Yun Jung-un, she's not here, but she has been making whole thing possible. And also we have 2 interns who probably you guys have interacted intensively. And then we have also members from IBS like Sung-Jun Lee and Bang Mi-hyuk, and they've been making all your foods possible. So let's thank them again. And also Professor Seok Kim took care of all the lecturers, and also Professor Kim Na-gu took care of the the gong shows, which was really interesting, and a lot of people gave a lot of interesting poster sessions. And let's close the school, and there is another one at the homepage in coming December at YITP Kyoto, Japan. So if you want to learn more, maybe you can apply again. Thank you. Okay, let's close the school. And I hope for all your safe journey back home. Bye.
sense, yeah, I agree that there's no medianness only comes from existing stream just because of dimensionality. Yeah, but maybe in further down there might be higher notion of no medianness. I don't know.
But because I don't understand. So because okay, in sorry, in 5 dimensions, you can try to write BDB.
Yeah.
And okay, because of I don't remember now the reason, but you need two different just for the dimension.
Yeah, B is the even form. So
Yeah, you can get it by parts. Okay. So okay, you need two different ones, but is it so different having two different ones having the same one?
But then you can regard that as a